Morning, everyone. Just few still joining in there now, so we'll give it 30 seconds to a minute and get going. Okay, I think that's mainly everyone in. Anyone left to join will be able to get in quick enough before it gets going. Thank you for joining us on this webinar on analog filtering techniques. The presentation is roughly about 17 minutes or so, and as usual, if you have any questions, just put them into your chat and we'll get to them at the end.
Welcome to today's tutorial. Let's get started. Let's look at our agenda. Today we're talking about analog filtering techniques. We'll start by talking about why good analog filtering is no substitute for poor installation practices. We'll talk about when and where you should filter, filtering that's available built into the OCS I/O configuration, and then filtering that you can implement in your logic. We'll also talk about different types of filters such as low-pass filters, as well as techniques like sample averaging and change limiting. We'll also talk about the advanced filter options available on the OCS that you may want to implement in your application. There will be video demonstrations throughout, and as always we'll finish with a Q&A session. Why do we use analog filtering? Analog signals provide key feedback to a controls engineer as they attempt to design a control system for a machine or a process. It's important that the feedback you receive from the analog signals is representative of what's really happening in the control system so that you can monitor and control that system properly. It's not uncommon for the signal to be more unstable or noisy than you would like, so that is something as a control engineer that you need to address. It's important that every effort should be made to eliminate that source of instability and the source of any noise before we start the filtering process. First of all, what are some of the sources of instability or noise? One thing that could cause this is a mechanical issue in the machine. This could also be caused by electrical noise riding on the signal. In this case, we need to ask, are proper wiring techniques in the analog signal chain in place to ensure that the impact of that is minimized? We must also ask, did we select the right cable? With analog wiring, usually that means shielded twisted pairs wiring. If we do have shielded wiring, have we grounded that shield properly, as an ungrounded shield is an antenna for noise. Cable routing is also important here. We should route our signal cables away from our high voltage cables. We don't want them running side by side in a cable tray if we can help it. When they do intersect, we want them to intersect at a right angle. We need to pay attention to these issues before we start doing any kind of filtering techniques. Once we've taken care of the installation and the design, we may need to implement some filtering. What we're talking about is digital filtering of analog signals. The analog to digital conversion is done in the OCS hardware itself. There are 2 points at which you can perform your analog filtering. The first point is in the I/O configuration, where you have the option to configure filtering for your analog signals. This is performed after the A to D conversion, but before that value is written to the %AI register. That's done by the OCS firmware. The second place you can perform your filtering is in your logic program. Here, you're taking that AI value that came in from your analog to digital conversion and performing filtering on that value. Then you will create a new variable in your program that you're going to use in your control algorithm. Now let's look at types of analog filters. Let's start with a low-pass filter. Here we'll talk about a low-pass filter that is implemented in the OCS firmware as part of the I/O configuration. A low-pass filter is designed to allow signals lower than a set limit or that are not changing rapidly to pass, and it's going to attenuate the signals that are changing rapidly at a higher frequency. For the OCS in the hardware configuration, you can set up a digital filter that will perform that level of attenuation. For this, you have to set a filter constant, which can be set between 1 and 7. If you set that filter constant to 0, it disables any filtering, and therefore the OCS firmware will just do the analog to digital conversion of your signal and will directly pass that into the AI register. If you implement the filter constant between 1 and 7, then it's going to perform that level of filtering before it writes the AI value. Let's look at how that filtering works. Let's say we have a filter constant with a value of 1. What that means is the OCS firmware is going to do an analog to digital or A to D conversion. Then it's going to compare the current A to D converted value with the previously stored AI value. And then it's going to give each of those a weight of 1 or an equal weight. Then you will complete the following calculation to get your current AI value. If you set the filter constant to a value of 2, now the previously stored AI value has double the weight compared with the new conversion. If you set the filter constant to a value of 3, it would have triple the weight, and so on. So that's the algorithm that's used, which you can see graphically shown on the screen, where we have a percentage step change on the y-axis. Along the x-axis, we're graphing time in terms of the number of A to D conversion scans. Here, you can see the lower your filtering value, the faster your AI register is going to rise to a higher value. But this has more potential for noise. While with a higher filter constant, it's more stable, but also slower responding. Setting our filter level allows us to balance these. Now we're going to demonstrate this in Cscape. Here I'm using an XL7 Model 3 that has 4 to 20 mA or 212-bit 0 to 10 volt analog inputs built into it. I'll start by going to Hardware Configuration and then Local I/O. I'll click under Config next to the I/O. Then I'll go to Module Setup and then Analog In, and you'll see here is where I can configure whether I want 4 to 20 milliamps or 0 to 10 volts for my input signal. Down here is where I can configure the filter constant between 0 and 7. Before I adjust this, let's look at my OCS that I've configured. Here we have a zoom in of a signal that's being generated by my I/O simulator to the left. That's being wired into the 2 mA inputs on my XL7, and I'm showing for the first analog input. I'm showing a zoomed in value of that signal. It's jumping around quite a bit, but keep in mind I'm zoomed in, so there's only a third of a milliamp of range shown on the screen. So that is my raw signal before filtering. Let's go back to Cscape. Now I'm going to make an adjustment to my filter value. Remember, when filtering we are balancing stability, which we get with more filtering, with response time, which we lose with more filtering. So a value of 7 is going to be the most stable but the slowest responding, while a value of 1 is going to give the least stability but with little loss of response time. I'm going to set a default value of 3, which is somewhere in the middle between 0 and 7. Now I have to download this change. Once that's complete, I'll go back to my OCS. You'll notice that the graph has started over again. That's because I'm sampling my analog signal and my filtered value every 50 milliseconds. So I can't use the retentive trend here. Instead, I'm using a continuous scope. So when I get to the end of this graph, it's going to continue to scroll, which I will cut to now. If you want to learn more about trends, we did a webinar on them recently, which you can view in the past webinar section on the Horner website. Looking at this signal, you can see we've added a lot more stability. Now I'll make a change to my signal to see how my response time has changed. You can see that I was able to make a change and it responds relatively quickly, but there is some lag there. That's how to take advantage of the low pass filter that's built into the I/O configuration in every OCS. Let's go through some of the other filtering options available. Next, let's talk about the moving average approach to filtering. Here we are taking a previous number of samples and getting their average. Each sample has equal weight. That should be more stable than if I was just looking at the analog value directly. On the right you can see a representation of this. Here we have 10 values that are stored away after every scan of the analog input. Then we do a simple average calculation where you sum up the analog value for the last 10 scans and divide that by the number of samples. In this case you'll have to involve some logic. Let's demonstrate how we could do that in Cscape. Here I've created a user-defined function block that performs all the averaging for me. In this UDFB I have one input and one output. The input is the integer value of the analog input that I'm going to be filtering. This variable is tied to the %AI register. In this second instance of the same UDFB, I have another analog variable that's tied to %AI too. Then I have another integer going out, which is my filtered value. The other input to my UDFB is the number of samples that I'm going to maintain in an array and the number of samples that I'm going to average together to come up with this filtered value. Now let's look at the logic within the UDFB. Because we're going to be creating an array in this logic of the last 100 values of my analog input readings, I need to do everything in this subroutine either in double integer math or in floating point math. I've decided to use floating point or real values. I'll start by taking my analog input that was passed to the UDFB and I convert and create a new variable that's a real equivalent of that. Next, I have a couple of things that I do on the first scan. This UDFB maintains an array of the last 100 analog input scans for that analog input variable. You may wonder what happens right after power up or right after we go into run mode. We won't have the last 100 values to deal with, so we need to build our array with values on the first 100 scans of the first 100 conversions. On the very first scan, all we can do is take the analog input conversion that we just received and pass it directly as the output to the function, or the output of the UDFB, because we only have one value to compare it with. Everything else in the UDFB is executed for every subsequent scan after that. First, because we want to maintain an array of the last 100 analog input values, we need to count up on the first 100 scans to ensure that we have our 100 values coming in. As we execute every scan and we receive a new analog input value in, they get loaded in this shift register. The input to the shift register is the real equivalent of our analog input conversion. The array itself is referenced here, and when we shift in a new value, we're going to shift in one position. That's how our shift register is configured. And for our direction, we're always shifting values left or up. To do our average calculation, we'll utilize a loop within this UDFB. To set up our loop action, first we must determine how many times we are going to work our way through the loop. By default, the number of times we're going to work our way through the loop is the number of samples that we were told to average. So if the routine was passed or the UDFB input was told we want to average the last 20 samples, then this max variable is going to have a value of 20. An exception to that, for the first 19 scans through the logic in this example, we don't have 20 values that we can add together. In this scenario, instead of going through the loop the full 20 times or the full 100 times, we'll only go through the loop for the number of values that are actually in our array. Once we get to 100 values, then we don't ever have to worry about that again. The last thing to do before we execute the loop is we must subtract 1 from the number of times that we're going to work our way through the loop. That's the offset we'll use when we're putting analog values from our array. We're going to set the loop counter to 0. We'll also set our numerator to 0 because we'll be adding numbers to that numerator, so it needs to start at 0 and end up at our total sum. Then we'll create our denominator variable, which is based on the number of times we're working our way through the loop. At the end, we're going to have a numerator, which is the sum of all our analog input values, and then our denominator, which is the amount of numbers we added together. We'll simply divide our numerator by our denominator, and that is our average. Here's how that loop works. This is the indirect move where we are pulling out each of the analog input values one at a time as we go through the loop. That then gets copied to a variable that gets added to the numerator. Then we increment our loop counter and we check to see if our loop counter has reached its max value. If it has not, we jump back to the start of the loop. If it has reached its maximum value, it means we've gone through the loop as many times as we need. Then we do our division of our numerator divided by our denominator, and then convert our real result into an integer value, which is the output of our UDFB. As I've done this logic once, I can then use it as many times as I need for my analog inputs. To illustrate the impact of the averaging technique, I need to reset our filtering for our low-pass filter to its disabled value of 0. Again, I'll go to my hardware configuration, then local I/O. Then again I'll go to my config, then module setup, and then analog in. And then I will set my filter constant back to 0. I'll now download that to my OCS, which I will do off screen. Now I'll go to the OCS. Here's my main menu. I'll go to the graph for the second analog input. That's the raw analog input value coming in from the %AI register and mapped directly to an input variable. On the graph below, I'm showing you the result of doing an averaging of the last 10 readings. You can see significant improvement in the stability of the signal. Now I'll go back and change the number of samples we are averaging to a value of 100. It's going to significantly impact the ability for the signal to respond quickly. So here we're getting added stability but also slower response time. So that's how you use a moving average approach to increase the stability of your signal. Next, let's talk about some other techniques that we can use. The next filtering technique I want to talk about is limiting. Here we're limiting the step response for any reading that we will allow to occur. We want to limit large changes in the signal because that could potentially be noise. By using the limit technique, we'll establish the maximum instantaneous change in reading that we will allow. Every time we do a reading or take a look at the current analog input value, we'll compare it against our current average or the current filtered value and see what the delta is between those two values. If that delta is greater than the maximum that we've decided to allow, then we'll limit our newly filtered value to only change by the amount that we've established as being the maximum. On the right, I'm showing the equation. Here, y sub n is the new filtered value, y sub n minus 1 is the previous filtered value, and delta v sub n is the change in value for the current reading. Delta v is the difference between our current reading, which is x sub n, and the previous average or previous filtered value. Again, we check to see if that delta vn is greater than our delta v max. If it is, then we limit delta vn to be equal to delta v max. Using this technique, we can help limit quick transient responses without losing much response time. Next, let's talk about some advanced approaches and filters. One of those is the Butterworth filter. A Butterworth filter is a sophisticated filter that's based on some advanced mathematics. Created in 1930, it improved upon previous filters by maintaining steep attenuation in the stop band, but eliminating any consequent ripple effects in the passband. You can implement something like this in the OCS using advanced math functions. Here is an example of this. Here is our equation where we have y sub n, which is the filtered value that you're going to calculate. You can see that filtered value is based upon the last couple of filtered values that were previously calculated, so you need to maintain those in your OCS memory. You also have x sub n, which is your current analog reading or your new conversion. All those values have coefficients associated with them, which you can calculate, shown in the blue box, where variables are dealing with your cutoff frequency, your level of attenuation, and your sample rate. After working through those calculations, you could very easily in OCS logic create a UDFB with a configurable cutoff frequency and a configurable sample rate, and would apply a second order Butterworth filter to an analog input signal. This would give you the benefit of good attenuation, but also a stable signal in the area of the signal that you don't want to change. Thank you for joining us for today's tutorial, and the Q&A session will begin shortly.
Okay, just a quick check on the questions panel. Currently not seeing anything there, so I'll take you back to my screen, which you should hopefully all see now. So we do have custom fonts coming up next week, followed by using WebMI as a large screen production monitor, our part 4 of our IEC support, and then into Cscape recipe management. Registration is there as always. It'll be same time. Thank you to those who pointed out that there was an issue with the times on this week's one. We got that sorted and hopefully it fixed on screen for you as well. Just see if there's anything else. Is there no? By using a jump back in a program and creating a loop, is there no risk with a high amount of jumps to generate a watchdog trip? I'll follow up with you directly after the webinar on that. I'll just verify the amount first and get back to you on it. Other than that, I don't see anything else. Thank you all for joining us again this week after our break last week. And we hope to see you again next week.